welcome to our webinar series for the USACM Energy and Earth Systems. I'm the chair of this technical thrust area. Just a little bit about the technical thrust area is found on the slide. So we're free to join for USACM members. So I would encourage folks to join, and we cover a variety of topics listed here from climate to geomechanics to different types of energy, carbon sequestration, capture and storage, oil gas recovery, and so on. We have 4 more seminars lined up. They're on Tuesdays at the same time as this one, about every 4 weeks. So the next one will be Professor Valerio Lucarini from the University of Leicester, who will be talking about attribution of climate change and tipping points. And I wanted to, before we get to the talk, I wanted to do a little bit of an advertisement here that the technical thrust area is organizing their first thematic workshop September 22nd through 24th, 2025 this year. It'll be held in Austin at the University of Texas at Austin, and the title is Artificial Intelligence and Digital Twins for Earth Systems. Unfortunately, didn't put the link here, but I will do that next time I show the slide. But there is a website up, so you can have a look at the topics of interest. There will be contributed as well as invited talks and posters. The abstract submission will open up March 1st and continue through mid-April. So I'll send some announcements when we get closer to those dates. So I'll stop my sharing here. So it's my pleasure to introduce today's speaker. So today's speaker is Professor Artem Korobenko from University of Calgary. He's an associate professor and associate head of research at the Department of Mechanical and Manufacturing Engineering at the University of Calgary in Canada. He holds a Schulich research chair and leads the computational fluids and structural mechanics group. He earned his PhD in 2014, followed by doing a postdoc at the University of California, San Diego. His research focuses on developing multi-fidelity computational methods for the analysis and design of complex systems in aerospace, wind, and marine engineering using large-scale HPC. He has a number of kind of accolades. So he's a former Fulbright Fellow and an Alexander von Humboldt Fellowship recipient. And additionally, he's the founding member and current president of the Canadian Association of Computational Science and Engineering, as well as a member at large of the USACM Computational Fluid Dynamics TTA, Fluid Dynamics and Fluid Structure Interaction TTA, as well as a founding member and co-director of the University of Calgary Aerospace Network. So the title of the talk is Advances in Modeling Wind Turbines with Variational Multiscale Methods. And I'll let Artem take it away.
Yeah, thanks so much, Irina, for your kind introduction. And I just want to make sure that everyone can hear me well and can see me and presentation. Yep. Okay, that's great. So yeah, I'm very, very excited to give this talk on recent advances in modeling of wind turbines with the variational multiscale formulation. And this is the development for the last, I would say, 5 years in our group together with multiple collaborators. And throughout this talk, I will focus on blade resolve simulations and going all the way to very recent work on the reducer remodeling. Just a few words about our group. So as Irina mentioned, I'm the head of the computational fluid and structural mechanics group, and wind energy part substitute about 1/3 of the activities in our group. Another work which is also related probably to this thematic workshop focusing on energy is our work on the marine renewables. So we work a lot on the hydrokinetic turbines. And another part is related to the aerospace applications, where we look to the various problems ranging from the low subsonic, like the air mobility, and all the way to the hypersonic flow in thermochemical non-equilibrium. So again, if you are interested, please check our website. Now, coming back to the today's talk. So first of all, I would like to acknowledge the a heavy lifting that was done by my former and current students, Dr. Haoyang Chen, Mr. Michael Ravensbergen, Mr. Abushan Regmi, and Mr. Sujal Dev. So Sujal is actually graduating this summer and will be looking for the postdoc position. So he's the one who was developing the reduced order modeling that I will be focusing on at the end of my talk. So again, if you have any opportunities for the open position, please let us know. Okay, start with the motivation. Why we need to do analysis of the for the wind turbines is pretty obvious. So I don't want to spend too much time on this. But again, we all know that the turbine keep increasing in size. They keep placed in the different environment, offshore at the foothills of the terrains, and the complexity of the physics getting more and more, right? And as a result, it is crucial and critical to have a predictive modeling tool that is able to predict the performance of the wind turbines, or actually wind farms, in these site-specific conditions. And in this talk, I will mostly focus on the fluid mechanics part, because I think this is one of the most complicated challenge. If you look at the recent review articles from the wind energy community, the outline of their challenges include the wake structure interaction, the wake meandering, the high Reynolds number flow, the terrain-induced turbulence, stratification. So you see many challenges originate from the fluid mechanics part. So the bulk of this talk will be dedicated, how do we accurately model the fluid mechanics? And the development that we do for the wind turbines is also applicable to the general environmental flows. And here is an example of how can we, or like I would say, a problem that currently is in the US, right, in California, and here in Canada, in Alberta. We recently had a huge wildfire in Jasper National Park. So accurate prediction of the environmental flow is critical. So going to the mathematical formulation, I will start with the set of the classical governing equation. So we look into the set of the incompressible Navier-Stokes equation. We are dealing with the stratified flows, which means we account for the temperature stratification, which is the variation of the temperature along the height. And again, there are, I would say, 3 different stratification regimes, namely neutral, stable, and unstable. And they're changing throughout the day. So it's very important to account for the change, because the heat flux from the ground changes drastically by almost 20%. And so if not accounted for that, the performance of the wind farm or the accurate modeling of the flow can be deteriorated. So we have this so-called the Boussinesq approximation for the Navier-Stokes equation. You see this term highlighted in green. And then we have an additional advection diffusion equation, which governs the transport of the scalar quantity. In our case, it's the temperature. In our formulation, we look into the 2 types of discretization, so spatial discretization, namely the finite element. So again, I'm coming from the finite element for fluids community, right? So in this talk, this would be the type of the discretization used, as well as we look into more advanced, higher order isogeometric analysis using either B-splines or non-uniform rational B-splines called NURBS. Here's a snapshot of the conforming finite element discretization for the wind turbine. So starting from this strong form of equation, we can formulate our classical Galerkin form for the momentum and the continuity equation, coupled with the additional transport equation, okay? So as we all know, the Galerkin form is unstable, right? And we also need to account for the turbulence. So this is where we introduced our first component to the model, which is the variational multiscale formulation. So VMS, the concept that was introduced by Professor Tom Hughes back in the 90s, and it shares some similarities with the classical LES approach. And I will just say a few words about, where does it fit in the context of the classical turbulence modeling, right? So if we look at our famous energy cascade, right, you can have your URANs, you can have your LES, right, where your discretization lies somewhere in the inertia subrange, and then you have a DNS where you're resolving all the way up to the viscous subrange. And so VMS is an LES-like approach, which means your mesh discretization will be somewhere in the inertia regime. Similar to LES, you start with the scale separation, right? So you decompose your space into the large scale or coarse scale, which is the model with the grid, and the fluctuations, okay? This will imply the decomposition of the test functions and the variables, okay? And then the idea is that you take this decomposition and you introduce it back into the Galerkin form, okay? And what you end up with is the two set of equations. One is called the coarse scale equation, okay? And the second one is called the fine scale equations. And so idea is that if I can find a closure model, right, or expression for my fluctuation, then I can introduce it back into the coarse scale and my system is closed. Now, is it difficult to do? Yes, it is, right? Because solving this fine scale equation is as difficult as solving your Navier-Stokes equation. So the strategy is to obtain the approximate analytical expression for your U prime and introduce it back into the coarse scale formulation, okay? So how do we do that? Okay, so we can reformulate our fine scale problem in terms of the projection operator, right? So if I rearrange the term and I put all of the small scales on one side and all of the large scale on another side, I ended up with the following set of equations, right? Where you can see on the right, right? When we regroup the term, we have a residual of our coarse scale, okay? And we also have this function psi delta, which guaranteed that our right-hand side is still infinite dimensional, okay? So this is just the way how you can look. And now again, depending on these projections, we can formulate our fine scale equation. In reality, however, we will be looking into the approximation of this fine scale problem, okay? Which is giving as following. So again, I refer you back to the original work of Professor Hughes, and then later in 2007, the work done by Yuri and Tom, where they introduced the residual-based variational multiscale formulation, right? So I'm skipping those very important mathematical details, but we can formulate the following approximation, okay? And then we have a choice for our small scale quantities. So the simplest choice is we assume that our fine scales are quasi-static, okay? So the time rate of change of those is 0. And another assumption is we use something called the algebraic subgrid scale model, which means all these functions goes to 0. You can refer to the work of Ramon Codina and colleagues, where they also look into the time-dependent subgrid scales and the orthogonal subgrid scale model. But for our case, the simple model works just fine, okay? And with that, we can express our small scale quantities, okay, for the velocity, pressure, and the temperature as the proportional to the residual of the large scale, and this proportionality factor is given through this stabilized parameter tau, right? So this is the basis of the stabilized finite element method. For our tau definition, we use the classical diagonal formulation, okay, where again, the each of these stabilized parameter is giving us as follows, okay? So again, I do refer to the work of Professor Hughes and actually Professor Tesdiar from 80s and 90s, where they look at the origin of the stabilized finite element method. But yeah, that's our expression for the small scale. Now, because it is proportional to the coarse scale residuals, the formulation will be consistent. In a sense, as your residuals goes to 0, your small scales goes to 0, so you're not introducing any artificial parameters into formulation. Okay, so now let me show you what is the final bilinear form will look like, okay? So first of all, we have our classical Galerkin form, okay? As before, it is there. Then by introducing the definition of our small scale quantities, the first term we will have is so-called the SUPG term, right? So streamline upwind Petrov-Galerkin, okay? This term is actually similar to the classical cross stress from your turbulence modeling, right? Because it's nothing but the product of your U prime U, okay? Then another term that we introduced, it's called PSPG. It's a pressure stabilized Petrov Galerkin. So this term will allow us to use the equal order interpolation for the velocity and pressure, and those satisfying the Babushka-Brezzi condition. Next, we also have the term which originates from the least square on the incompressibility constraint. And finally, we have additional VMS term, which looks like another cross stress, right? And finally, the term that looks like the product of the U prime, which looks similar to the classical Reynolds stress from the classical turbulence model, okay? And this is only for the momentum and continuity. And then you have the SUPG term originating from the transport equations, the term associated with the Boussinesq term, and finally, the interaction between the small scale temperature and the small scale velocity, okay? And you have the right-hand side where you have the body force and traction boundary condition, if any, okay? So this is the complete fluid formulations or turbulence modeling that we will be using in all of the problems presented in this work. Now, another important ingredient that we need to account for is how do we deal with the flows near the surface, okay? If we're dealing with the blade resolved wind energy simulations, right, we're looking into the flow around the blades, or if we're simply looking into the flow over the complex topography, we also want to satisfy those no slip conditions at the surface. And for this purpose, we instead of using the strong no slip boundary conditions, we use so-called the weakly enforced Dirichlet boundary conditions. Again, the original idea was introduced by Tom and Yuri, and later we actually extended these formulations for the stratified flows, right? So the formulation is given here on the left, right? So you introduce this so-called consistency, adjoint consistency, and penalty term, for both for the velocity and for the temperature, which relax the requirements on your boundary layer resolution and allow your flow to sleep on the coarse boundary layer regime. But again, as you refine, you're exactly recovering those no slip. Now, I want to highlight this term tau b, right? So in the original definition, this this parameter was introduced using the following formulation, right, as a proportional to the the flow property, this constant C, which is estimated based on the inverse estimate and inversely proportional to the mesh size. But then in the early work, Tom and Yuri, they also introduced this so-called wall function based weak BC, right, which shares similarities with the classical wall modeled LES approach, okay? And in our work from 2022, we also extended this wall modeled weak BC for the stratified flow formulations, okay? So giving here, right, you can see, this is your classical Spalding law of the wall, and then we extended the same thing for the temperature, okay? And this also allowed us to introduce the surface roughness into the formulation, which was very important, as you will see in some of the examples later on, okay? So the complete system of nonlinear equations, it's solved in time using the generalized alpha method, which is the implicit, unconditional, stable, second order accurate method. On every time step, we solve a system of nonlinear equations using the Newton-Raphson method. So you can see linearization, right, of the construction of your Euler-Jacobian matrices. And then at every nonlinear iterations, we solve the system of linear equation using the general minimum residual method introduced by Saad and Schultz. Okay, so now let me go and show some examples related to the turbulent flow, okay? And then after that, I will go to the blade resolved wind energy simulations. And after that, I will introduce a multi-fidelity and reduced order modeling formulation that we recently developed for this type of application. So I will start with very classical channel flow, right, which is provided over here. So this is called the stratified channel flow. And here we are comparing our VMS formulation with the direct numerical simulations, right? So you can see the discretization used by, our model as well as the DNS. Okay, so we look at the different stratification regime, right? So given by the Richardson number as well as the friction Reynolds number, right? And here is some of the results. Okay, so this is called the like a medium stratified flow. So the Richardson number of 120. And in this test case, we also tested an idea for our stabilization parameter tau, because if you remember on my previous slide, I said we're using so-called the diagonal formulation for tau. However, if you're dealing with the stratified flows, you actually have a coupling in your momentum equation with the temperature through the Boussinesq term, and that coupling should also be reflected in your definition of tau. So this is, again, idea that UDI and our colleagues introduced back in 2015. And recently, we also tested this for this type of flows, which for this test case, we found actually almost no difference between using the diagonal definition or introducing this coupling. But the most important thing, if you look at this problem, what it has something called linearization. So you can see, right, this is the slice of your domain, and you can see you have these patches of the laminar flow. And with the classical model, it's very difficult to capture that, because what should you use? Should you use the turbulent model? Should you use the laminar model? Should you use some kind of transition model? In our case, without any tuning, and with the same set of parameters, actually, that's a very important point. All of the examples I will be showing, we use exactly the same set of constants. So there is no tuning or anything to pretty much problem-specific approach. So the formulation is pretty robust across the range of applications. And you see, the top is our VMS and the bottom is the DNS. And so qualitatively, we are capturing quite well these linearization patches. And same if you look at the first and second order statistics, quantitatively, we're also quite good. Now, I just want to highlight that these triangles, this is a DNS with the Richardson number of 0. Okay, so this is the like a non-stratified flow case, just to show you what happens to the flow when you introduce the stratification. So here the DNS is actually these crosses, right? So we are matching those quite well across the different quantities. Okay, here we look at a slightly higher friction Reynolds number, right? Where we look again into the classical weak BC formulation compared to the wall function based weak BC. So again, we look at the first order statistics for the velocity and temperature, but we also look at something called the gravitational Richardson number. And we can see that by introducing this wall function based weak BC, we're actually having a better agreement with the DNS result. So this is the formulation that we try to stick through the throughout our work. Okay, now this is just another view on the second order statistics related to this flow. So again, we're getting the results pretty close to the DNS on the way coarser meshes, which is very important. Okay, now another test case is more relevant to the like environmental flow modeling. So this is called the stable boundary layer flow. So which was conducted as a part of this base experiment. Okay, so you have this domain, right, characterized as follows, right? And you have the surface cooling. So what will happen over time, you will develop something called the inversion layer or something called the low level jets. And you will see it's actually quite hard to capture that if you do not have a wall function based boundary conditions at the bottom. Now, and another thing I should mention, a previous test case as well as this test case, we are using the quadratic B-splines at the discretizations. Okay, so I think that was an important point I should have made. Okay, so this is the setup, and these are the results. Okay, so on the left we see the slice, right, and so this is what I refer to, right? So you have the formation of this so-called the low-level jets, right? You actually would probably experience that when you fly on the airplane and you see a very tiny cloud, and as you pass that, there is a pretty significant level of turbulence over there. Like in Alberta, we have that a lot, and if you are using your classical weak BC, right, or strongly imposed Dirichlet boundary condition, is very difficult to capture this low-level jet formation. But with the wall-modeled weak BC combined with the VMS and quadratic B-splines, we are capturing that phenomena quite well. And again, here we look at some quantitative results. So the gray area here, that's actually a large study from multiple models, like mainly LES, of course, that was conducted as a part of this base experiment. And we're agreeing quite well with those studies on a way coarser meshes, right? So the grid resolution that we're using, because of the weak BC, allows us to use a coarser grid resolution. Again, some different statistics, right? So, which is actually quite hard to achieve, right, accurately. So this is your time histories of surface momentum and buoyancy fluxes. So yeah, you can argue that, yeah, we are kind of a little bit outside of the predicted test range, which we are further looking up. But if we look at the so-called the K-type parameterizations, we're getting quite good result. But again, this is still work in progress, and we're investigating what exactly impacting the results in this case. Okay, now keep moving. The next test case, was the flow over the complex terrain. So this was the experiments done in Denmark on the ballooned hill. So you can see the hill over here, right, with the different mast location. So we again used quadratic B-splines for this type of application. And here we look at the results, right? So this is the normalized velocity, right, along this hill. And here we're also comparing the results to other LES, RANs, as well as the mast measurement. And I would say that we are getting a pretty accurate results, including the region where you have a very sharp, the front part of the hill, as well as the lee side, right, where you start having this recirculation. Now, on the actual top, which is like a flat part, we're a little bit outside of the, error bounds for the measurement. So we're still investigating what could be causing that. But overall, the results, especially compared to the other studies, like you can see that our blue NURBS, right, way better matches the measurement compared to other studies. So that was pretty encouraging. Okay, and again, just another look at the different mass locations of the velocity. So you see a pretty good agreement over there. And the next test case was a part of the collaboration with the group from Notre Dame, where they look at the flow over the Perdigão terrain. So it's a large field test experiments that was done in Portugal, and it's still ongoing. So it's characterized by these two large ridges, right? And we look at the flow behavior around those ridges. This was just a preliminary study. So now I'm actually in discussion with Jacob Mann, who was heavily involved in this and doing lots of the measurements. So currently, Perdigão experiment has a huge database, including the mass data, which we are looking to compare. But this was like a preliminary study to see how well we can predict the flow behavior. And even this preliminary study gave us a hope that our formulation can handle this very complex flow behavior with a realistic terrain. Finally, so I showed a separate stratified flow simulation. I showed a separate complex terrain. So now can we actually combine those two together? And here we look at the stratified flow over a three-dimensional hill. Okay, with the varying Froude number, so kind of low level and high level stratification. Now, the interesting thing about this problem is that this is very common for the environmental modeling, right? So you can think about this hill to be maybe like an island, right? And you look at the flow around the island, or if you have maybe hurricanes, and in those tests, like in those cases, you have something called the hydraulic jump, okay? And that hydraulic jump is extremely difficult to capture with the classical model. And in our case, yeah, we are capturing that hydraulic jumps and the different level of, different level stratification quite accurately. Again, here on the left, you see the, the qualitative comparison, right? And you see as you change your Froude number, how the flow behavior are changing, right? For the 0.4, it goes mainly on the side. When you bump it to 1, it starts going more around, like over the heel, and so the flow behavior drastically changes. So again, some comparison with the theory as well as the experimental studies, right? So this is the hydraulic jump that I was referring to, and we can capture that quite well with our formulation. Okay, and this is just another view on this test case. Okay, so finally, now let me move to to the wind energy. Now, and again, the main reason I spend so much time on the fluid part, because in my opinion, that possesses the most of the challenges. Okay, and so having the accurate fluid model and turbulence model is critical, to predict the flow behavior around wind turbine. Now, for the blade result simulation, this is the work that myself and Yuri was conducting several years ago when I was, ramping up my postdoc at UC San Diego and moving to faculty position at University of Calgary. So I will just show a few snapshots what we achieved on that respect. But before I do that, I actually want to introduce another techniques that we had to implement in order to do blade result simulation. And this is called the sliding interface formulation. And the main reason for that is that if you look at let's say a single turbine, right, you have your tower, nacelle, and then you have a spinning rotor. So as a result, you need to account for this relative motion, right, with respect to the rest of the fluid. Okay, and so this is the idea that again was introduced by Professor Hughes and Yuri back in the days, where you split your fluid domains into so-called the moving and stationary part. And again, we extended that to multiple domains, including the stratification as well. And so what you do on this interface, you actually satisfy your kinematic and traction compatibility using the idea similar to your weak BC, where again, you have your consistency, adjoint consistency, and penalty term. So again, I don't want to spend too much time on this, but if you're interested, you can look at our review paper we've done back in 2018, where we discuss in details all of these techniques. And so some of the studies that we conducted, and I should point out that in this work, as I previously stated, I'm focusing mainly on the fluid part. So structural part is very important as well, and the coupling, right? So the fluid structure interaction. But in this work, I'm purely focusing on the fluid mechanics. So maybe next time I can speak more about the structural mechanics. So here was again an example of the at full scale 5 megawatt NREL wind turbine, which is slowly yawing into the wind. Okay, and the blade is free to deflect. And actually here, the rotation of the rotor is driven by the flow. So it's not a prescribed, right? And you can see as the blade, as the rotor yaw, you kind of recovering, you can getting into this, your expected power production, right? And here you can just see internal structures of the blade. So we were able to capture that. We also extended that formulation to the vertical axis wind turbine. So this was the early collaboration, with Professor John Daibiri. Back then, he was a faculty member at Caltech, where we were looking at the self-starting issue of the vertical axis wind turbine. So pretty complicated problem due to this downwind interaction between the blade and the wake, and your angle of attack keep changing from fully attached to fully separated. So a very challenging problem from the fluid mechanics point of view, and we were able to capture that quite well. Quite recent work as well was the incorporation of the atmospheric boundary layer flow, where we look into the multiple wind turbines. And here we incorporated something called the multi-domain approach. So here on the right at the bottom, you see we split our problem into the 3 subdomains. So we run the first domain, we collected the data at the plane, then we projected into the middle domain. We propagated, again, we collected the quantities of interest somewhere at the plane, okay, not at the outflow, but somewhere close to, and then we run our second domain. So that allows us to speed up our simulation, and you can see that the flow is pretty continuous across these multi-domains, and we were able to to predict the wake deficit. And as you can see, even as it hits the second turbine, you still have a deficiency of almost like 25 to 30%, which is consistent with the field measurements and other reported study. But yeah, this was a blade resolved, atmospheric boundary layer flow hitting the turbine with FSI. Okay, so this was not just CFD, but it was a full FSI. So it was pretty impressive simulation. But and as I mentioned, yeah, I'm not even talking about the structural mechanics part or FSI. So I will just keep it here because we've done lots of work. So I just want to give credit for this and kind of point you out to these papers if you are interested more into the structural mechanics. But let me go to the next topic. So as I mentioned, the blade resolved simulation is great. You can capture your fluid behavior, structural behavior quite accurately. But the major bottleneck, it is computationally expensive. And in reality, if you want to look at the wind farm where you have hundreds, right, or farm interactions where you have I don't know, close to maybe even 1,000 turbines, to resolve every turbine individually becomes impractical. Okay, and this is where we introduced into our variational multiscale formulation the so-called the multi-fidelity modeling approach, and I will explain what do we mean by that. So we introduced something called the actuator line model. So this is again technique which been used since 2000. It was introduced by Sorensen and then colleague. And the idea is as follows. So here we look at the fully, blade resolved simulation with the conforming discretization. Now, the idea behind ALM is you take your blade, you replace it with something called the actuator point, right? So this is the line, you have these points, and at every point, you have the aerodynamic informations, or you have the blade profile, right? Let's say your whatever airfoil profile series you have. And so now what you do, you have your fixed background grid, okay? And now at every point, right, at every of these ALM point, right, what you do, you sample the velocity from the background mesh, then you use that sample velocity to calculate your aerodynamic forces using your blade element momentum theory. And then you take these aerodynamic forces F and you project them back into the background grid, right? Or onto the certain, it's so-called the Gaussian projection, right? So this would be your forcing term on the background grid, which will simply go into the right-hand side of your Navier-Stokes equation. So introduction of the ALM to the VMS formulation is natural, okay? And so, yeah. And so what you do, you pretty much repeat that as the blade rotates. You do that for every point. And so you're kind of mimicking the impact, or the presence of the blade on the surrounding grid. How good this method is? Extremely good. Okay, so here's one of the examples. So again, for more test cases, please refer to our paper here at the bottom. But this is the wind tunnel measurements of NTNU wind turbine, right? And here we are looking into the velocity deficit as well as the turbulent kinetic energy. And you can see that with our ALM approach, we're getting a pretty good agreement with both experiments and the measure and other numerical approach. Now, some of you can question, oh, but if you look at your TEEP, you are pretty off. And I actually probably know the answer why we are, because at that case, when we implemented ALM, we did not have any so-called the TEEP speed correction, right? Because when you do this ALM approach, when you get to the last point at the TEEP, you need to do a special treatment for the TEEP loss corrections. And in that case, we did not do. And so, we expect as we introduce that, we will have even better matching with the TEEP compared to the experiment. So, but again, overall, this was pretty encouraging. We also implemented recently stratification into this ALM VMS approach. So again, this is the very recent work. So here we're looking into the this baseline NREL 5 megawatt wind turbine. So we look at the rotor only at this case, right? So you can see we have this fixed Eulerian grid on the background. And here we're looking into the stable atmospheric boundary layer flow hitting this turbine. So this is the similar atmospheric boundary layer flow that we used for the blade resolved simulations, and we can accurately capture the power losses due to the ABL and the wake formation. So pretty encouraging. We also recently conducted the simulation of multiple turbines arranged in the array. And we're currently looking into the wind farm simulation. Now, for these simulations, the ABL profile was pre-generated. Okay, so our collaborator back in UCSD, Professor Sutanu Sarkar, he generated this ABL flow, which we were using for this study. But recently, we actually implemented a synthetic turbulence generation method, similar to what Professor Churchfield did for his wind farm studies, and what is used by NREL in their SOFA code. And so now we can generate the various kind of ABL profiles, and this is what we are doing for the wind farm test cases. So now this was the multi-fidelity approach, which saved a lot of computational resources. But can we do even better than that? And this is where I would like to introduce some of our very recent work on the reduced order modeling for the wind energy application. So again, this is the work we started about maybe 2 years ago. So it was a pretty interesting exercise, because when we were reading the literature and we were chatting with lots of colleagues, and kudos to Irina, who provided lots of suggestions about this, everybody was saying that POD-based Galerkin reduced order model does not work for the high Reynolds number flow, and we always wanted to see, okay, if this is really the case, and how it will behave for the wind turbine simulations. And what I will show you is that it actually works quite well for this type of flow problem. So and I would be happy to take any comments and questions regarding that, or any topic presented here. So approach is pretty standard. Okay, so we started with the, I would call the simplest method, right? It's your classical POD-based projection, reduced order model, where we collect the high fidelity snapshots. Then, we did the singular value decomposition, right? And then we extracted the desired number of modes, okay, to capture a certain level of energy that we are interested in. Okay, then we can construct this reduced basis, okay, and then we can do the reduction of our of our linear system of equations. Okay, so pretty classical, and I believe many of you are familiar with this approach. Again, this is just the how does the modes looks like for the cylinder, but I'm not interested in cylinder in this case. Okay, what we are interested in, can we actually use this approach for our ALM VMS formulations? Okay, so what we did here, so we use our ALM VMS, which means we are not resolving the blades, but we are representing them with the actuator line point, and we look into the several discretizations. So 4x4, 4 refers to the discretization at the rotor, and 4 at the wake, and then we look at the different level of discretization, like 412, 812, and 420. Now, on top of that, if you do your classical ROM, you would not get any speed up, right? Because you still, doing that matrix vector multiplication, which is, a similar complexity to your classical high fidelity. And this is where we also introduced the mesh-based hyper-reduction approach. So what we did, we collected the snapshot using our finest mesh 4x4, but then our reduced order model was done on the coarser meshes, like 412, 420, and 812. And as you can see, with that mesh-based hyper-reduction, we're able to have a speed up of like order 8 to 14, which is pretty significant. Now, this table is just to give you a little bit idea of how difficult to actually predict the power production. Here we look at the different blade resolved, and finite volume and finite element. You can see there is quite sometimes a difference in the power prediction, which is mainly due to the velocity sampling. And this is where finite element method works extremely well for this velocity sampling. So you see, like, our error in terms of the power production is pretty good. Okay, so this is a few snapshots I would like to show you. So here we're looking into the full order model using our finest discretizations, okay, together with the full order coarse model. And you clearly see, as we go to a coarser wake refinement, we could not, as accurately capture the velocity deficit in the wake, right, as you can see clearly here, which is again consistent in your ROM formulation. Okay, now I should also mention that our ROM is the consistent ROM, which means it used the same stabilization parameter as your VMS, and that actually provides you an amazing functionality, because it is a priori stable. Okay, which means you don't need to impose any additional pressure supremizer or anything else. So that's actually what we're using here. So just consistent ROM without any additional pressure supremizer. Now, at the very bottom, this is the ROM with the mesh-based hyper-reduction. Okay, so we collected the snapshots on our fine mesh, and then we project them into the coarse mesh. Okay, and we use for the ROM our coarse mesh. And you see, so first of all, we're getting about 8 times speed up compared to the full order model. And if you can look at the velocity right deficit, we actually capturing way better, right, the velocity deficit in the wake when compared to the full order model computed on the similar mesh. Now, maybe another look on this can be done here. So again, we look at the velocity deficit, okay, here we are comparing the full order model with a traditional ROM, right? So if I look at this green, especially in the far field, right, so beyond 4D, right, you see that your 412, you start lacking, right, you're not capturing that quite well. But if you introduce this hyper reduction, you're pretty much recovering your full order, a fine scale model. Now, we decided, okay, let's push it even further. Can we look at even coarser mesh, right? So here, let me point you to a 420 and 812, okay? So again, we're using the snapshots from the fine mesh, and we're doing the mesh-based hyper reduction on the coarse mesh. And the result is pretty amazing, right? And keep in mind that the Reynolds number for this case is an order of millions, okay? And we're only using 10 modes, okay, for this problem. And you can see, like, yeah, if you start looking into the far field, your coarse full order model, let's say 420, yeah, it's pretty off, right? So you're not capturing that wake deficit. But if you're doing the hyper reduction on the same mesh, right? So 420, right? This purple line, you see we are recovering quite well the full order model. However, the speed up we're getting compared to the full order model is almost 13 times faster. So pretty impressive. And again, this is the work in progress. We're actually planning to submit a paper either this week or next week to CMME about this consistent ROM. So feel free to take a look at that, and we will upload it to archive as soon as we submit it. So again, I have probably maybe like 3 more minutes left. So I just want to highlight some ongoing work and that we are looking at. So first of all, I'm actually, our group is the part of the IEA Wind Energy Task Force 57. It's called JAM, Joint Assessment Model. So it is led by NREL. And here we're looking, it's kind of also associated with the Awaken project. So I believe many of you might be familiar with that. Here we're looking at the, how does the various tool capturing the flow around the wind farms and interactions between wind farms and wind farms. So this is I think the test sites in Oklahoma, if I'm not mistaken. And as a part of this task force, they provide us with the data that we can use to do this analysis. So again, it has the complex terrain, it has the farm-farm interaction, it has the stratification. So very interesting problem to deal with. And our group, I'm actually a Canadian lead on this task force. And so I do encourage, many more people to join and participate. And if you have questions, please let me know. I can point you to the leading manager from NREL on that. Again, this is another, wind farm simulations we are looking at, which is your classical Lillgrund wind farm. We're also looking into the, the turbine performance in the complex terrain. We're looking into the effect of the tower and nacelle. Another, collaboration that we're currently leading with the group from Italy is to couple our BMS formulation with a mesoscale model, right? and the common practice in the wind energy community is use something called the WRF, right, WRF model, where you do the mesoscale coupling so that your boundary conditions comes from this weather prediction model. So I'm also looking for collaboration on that respect. We're also extending the ALM formulation for the vertical axis wind turbines. And again, I just want to highlight once again that the activities in our group is not just wind, but we're looking a lot into the hydrokinetic turbines, as well as the various aerospace applications, from low subsonic to the hypersonic flow in thermochemical non-equilibrium. We are looking for collaborations. We have multiple fully funded MSc and PhD position in our group. So again, we work hard, play hard. We also have a various student mobility program, which is quite good in Canada, which means we can host students from across the world, and they will be fully funded by Canada. And that can be done up to 6 months. This is supported by the MITEX Global Link. And at the same time, I can also send students abroad fully funded by Canada for up to 6 months. So and also we have an opportunity for joint funding, and yeah, we are looking for those collaborations. And this is the last slide. So thank you very much for your attention. Thank you very much for inviting me to give this talk, and I'm open to answer any questions. Thanks.
Great. Yeah, excellent talk. So I would normally say clap, but we're virtual, so I'll try to find the clap emoji here. But are there any questions? So I had a few questions, so I can kind of kick this off.
Sure.
Regarding the hyper reduced ROMs, so if you just have incompressible Navier-Stokes, the nonlinearity is just quadratic, so you can pre-compute everything. Is the hyper reduction needed for the turbulence modeling piece? Is that, or like the VMS part? Is that why you need that, or?
The hyper reduction in our case comes from the speed up, because if you just use your traditional ROM, you would not get any speed up, like
Even
at
if
all.
you because I mean the nonlinearity is quadratic, so you can pre-compute that quadratic, like that tensor, if you keep reproject. So I'm just curious but maybe you cannot if you have nonlinearities in the turbulence model. Maybe you cannot pre-compute.
Yeah, you can pre-compute that tensor, and I believe this is what the group of Karen Wilcox is doing. They're pretty much pre-computing this tensor. We are doing the other, like we're not doing that yet, right? So we are actually collecting the snapshots, doing the SVD, extracting, and we are constructing those matrices. And because of that, the computational cost is pretty much either equal to FOM, or sometimes it can be even more expensive than FOM.
Yeah.
And so now I visited Professor Wilcox recently, and so we are discussing how to use their approach to in the context of the VMS. So we have some collaboration going on that.
Yeah, I mean, I would maybe recommend that because the hyper reduction can introduce error and instability, and so you would avoid that. I was also curious, the results you showed, were they predictive? So like, was the ROM run at different parameters than the training, or was the same?
It was run at the same parameter, but outside of the training range of the
Okay,
time
so
step.
different times.
Yeah, so now we actually that's an excellent question. So now what we are doing, we actually run that at the different Reynolds number, and we see, can we actually, like incoming velocity, right? So, and see if we can actually do the prediction in terms of various parameters. Because again, Professor Farhad in his paper, he highlighted all of the challenges associated with with the POD based ROM, including the transient. Okay, we're also looking right now how well we can capture the transient regime. But even apart from that, I haven't seen anywhere in the literature the ROM has been, like POD based ROM, being used with a high Reynolds number. Like everything that I've seen so far is limited to like a cylinder flows, maybe 1,000 or close to that. So unless
I
I'm
would
missing.
say, I mean, Charbel's group has done, they tend to do compressible flow. They do have some examples, but they were doing reproductive for a while. And now more recently, I can send you some references, but I also want to mention, we have a paper where we show that there's some benefit sometimes in using different stabilization, not in a VMS framework, but just more classical stabilized methods. for different stabilization for the ROM than the full order model. So I can send you
Okay.
that. Yeah.
Oh yeah, I would be very curious. Yeah, because it's still open
It's
question.
not
Yeah,
consistent then, like you say.
yeah,
It
but
depends.
do you really need this full consistency? Like, or is it, let's say, SUPG only is enough, right? Do you need to look
Yeah.
at those extra VMS term associated with it? So yeah, we are looking into that as well. Yeah.
So other questions? I guess the talk was very, very clear.
Overwhelming, probably. Again,
Oh,
it
well,
is
no,
recording,
it
so
it
yeah,
was great.
feel free
I
to
guess I'll
send
ask,
me
yeah, I'll ask
questions
one
or email.
more about the first part. So when you do the VMS approach, um, it's sort of like a reduced order model for the DNS, as you said. What sort of savings do you get with the VMS versus DMS? DNS?
Oh, yeah, you look at the grid resolution that we can achieve, right? So
Oh,
that's
okay.
so there was like an order of like I think the comparison we done for the stratified channel, I think for the DNS it was about 2000 times I think another 1000, etc. We're getting that with like 64 cube, right?
Okay.
With the tremendous save on the on the computational cost associated with the mesh. And again, this is not just due to the VMS. This is due to
Due to the grid.
the weakly enforced boundary conditions, right? That's number one.
Oh,
But
right.
another benefit of VMS, if you compare to the classical LES, is there is no tuning, right? There is no this artificial, viscosity that you have to tune for every problem setup. I know there is also ongoing work in the LES community to get rid of that and pretty much avoid the tuning. So there's like a tuning-free eddy viscosity model that was also introduced. So, but again, I think VMS really possess a huge potential for these type of problems. Yeah.
Okay. Last opportunity for questions. Oh, here's a question in the chat. Um, Mahesh, you can unmute yourself if you prefer. Just ask it.
Or I can speak it out if that's okay as
Oh,
well. So yeah.
Yeah. Hey, Artem, it was a great talk.
Thank you, Mahesh.
Could you comment on if the code is GPU enabled and like what is the cost of the simulations that you're showing, like particularly the wind farm simulations with actuator line?
Yeah, absolutely. Yeah, so that's actually the main critics of this, right? So currently, it is a CPU based only. So we are looking into the GPU computing because the bottleneck is your linear solver. So that's why we, step out of the, blade result because yeah, it's just unaffordable. Now, ALM VMS provide a significant speed up. So let's say in a 24-hour, we probably can get maybe, a 2 flow through a wind farm, which is still pretty slow. Okay, because if you talk to the industry, first of all, the industry practice is to use the analytical wake model. So they don't even look at this ALM or actuator disk model. But so now that's why we'll start looking into the ROM. But in parallel, we're also looking into the GPU accelerated computing.
Right.
And even on top of that, we have some recent collaboration with the quantum group from the University of Calgary. So we have a big quantum city, Professor Barry Sanders, who is leading that, where we're looking into the quantum linear algebra. So again, it's very early, and I'm not gonna put any claims on that, but we are looking into this even more advanced algorithm for the linear problem.
And
so yeah,
what are you looking into a particular programming model for doing the GPUs, or are you going to churn out your own GPU?
We have some ideas. I don't have a capacity, so that's pretty much a very standard bottleneck. Like I would be very happy to collaborate with someone who is focusing specifically on the computer science part, on the the software part, and help us to really boost the linear solver performance. Because either we completely offset it to either Patsy or some other stuff, right? Or because currently everything is in-house, and I know there are lots of open source platform that has more advanced linear algebra packages, but this is currently the bottleneck. So currently is not up to the industry standard. Like that's why if you look at Nreal, they have this exascale initiatives for the wind farm, and again, they look at the GPU accelerated computing, etc. So yeah, I don't know if I completely answered your questions, but yeah.
Yeah, you did. And it was a really great talk. Yeah, thanks.
Thanks, Mahesh.
I'll just add, I mean, like we produce a library called Cocos that enables you to make your code ported and run on CPU and GPU. If your code is C++, it's easy to relatively easy to integrate.
It's Fortran. It's Fortran.
Oh, well, okay, then your options are more limited. Okay, then you'd have to do OpenACC. But actually, the linear solvers and PETSI and Trilinos and various, they've actually improved quite a bit for GPUs. You can get actually speedups now. So that we've seen that ourselves with the
that's
Trilino.
what we are looking like. My students pointed that out, and so we're looking into that because
it was a big problem for a long time that the solvers
it is it is.
All right, well, we're at time, so thank you, everyone. The next presentation will be, I forgot, it will be in February. I closed my slide, so I don't have the exact date, but I will send an announcement. It will be 4 weeks from now, and hope to see some of you there. Have a good rest of your week.
Thank you, Rena, and thanks everyone for attending. Bye.